Welcome to this mini lecture on distributed photovoltaic electricity generation, system types and sizing. This falls under the category of what is also known as solar electric, and this lecture was originally intended to accompany the modules in photovoltaics for Bellingham Technical College's CENG 220 Energy Generation and Conservation Winter 2022. Okay. When we talk about distributed photovoltaic systems or solar electric systems, what we mean by the term distributed is systems that are intended to be used for single buildings, small campuses, maybe a barn, a facility, maybe in a rural area where utility scale electricity may or may not be available. Of course, distributed photovoltaic can accompany grid scale power, but a utility scale photovoltaic system such as a solar farm, some big installation that's intended to generate electricity for multiple different users or to be transported over the grid to multiple different areas, that larger scale generation effort would be what is called utility scale. We're focusing on the smaller scale, a system that's designed for a single home, a single business, a single farm, or a single hotel, resort facility, something on that scale that has very unique site characteristics and is producing power for a very well-defined need, usually a single user or group of users that have similar requirements. So on the downside, typically there's less money involved, so budget is a much bigger factor in this type of system design. But on the plus side, we can tailor a system that meets unique needs and not have to meet everything that a utility scale generation facility might need to meet. Okay, with that little intro, we're going to start with what are the different types of photovoltaic systems used for residential and commercial applications, which means for distributed systems. So first off, we have the type of electrical power we're generating. We can either have DC or AC, direct current or alternating current, in terms of the loads that our system is powering. Obviously, photovoltaic cells are going to produce DC as opposed to a rotating turbine generator, which produces AC. So your solar cells are always going to produce DC, but you can use that DC power to power either a DC load, to charge a battery, which is DC. It takes a DC charge, or you can run that through an inverter and transform it to alternating current and power anything that you would power with your normal AC sinusoidal waveform that comes from the grid. So your systems are basically going to divide down into, do you take your DC photovoltaic energy and run DC appliances and charge batteries? Do you turn it into AC? Do you do a little bit of both? Next distinction is, are we directly powering a load right from the solar panels, maybe with a converter match, maybe a DC converter match, or possibly putting it into an inverter and powering loads directly? Or are we going to store some of that electrical energy that we generate from our solar cells such that we can use it later and in whatever form we want? So we either directly power loads local, either a DC motor or AC loads in our homes off of an inverter, or direct to the grid. All of those would be direct powering of loads via a converter or inverter, versus we take all of our electrical energy that we're generating from our solar panels, we may alter the voltage a little bit through a charge converter, and we charge batteries. Then when we need to power a load, we draw down from the batteries. So there's that intermediate storage. So there's advantages and disadvantages to both systems. Very, very simple systems such as pumping stations on ranches, especially out in the desert where you may have to pump water from a great depth. During the summertime, when you have a lot of sun shining, you might run a DC motor for a water pump directly from a photovoltaic panel. So when the sun shines, the pump can come on, plenty of power, right when you need it, when your herd is thirsty, presumably, So there's a match to your energy availability and your need, as opposed to maybe someone who is living in a remote location who was using a standalone photovoltaic system to power a business or home and would maybe like the lights and the heat on at night in spite of the fact that obviously their cells are not producing. Which brings us to the last category, which is standalone versus grid connected. A lot of the growth in the distributed solar photovoltaic market has been in grid direct, which means someone connects directly to the grid and effectively is a co-producer along with the electric utility. Advantages to that are depending on the types of regulations and subsidies in the local area. You might actually be able to sell your solar generated power to the utility for a higher price than you buy power from them. So you could maybe make a little money, and that's known as feed-in tariff systems. If you live in a place that doesn't have that, you will at least probably have access to what's known as net metering, where basically you only pay for the power that you use. So you generate power from your solar cells, your solar modules. That power goes to an inverter, converts to AC, and then it goes to the grid or it goes to your loads, and you only pay for the net difference in the power that you get from the utility versus what you generate. Great things about grid direct and grid tied systems is you have the grid to back you up. You don't have to generate all of your own needs. You can produce power effectively for the grid. Someone will make use of your generating capability even if you don't. You might make a little money on it. Downside is when the grid goes down, so do you. The last thing that we can afford from a safety standpoint is to have an unknown generation source. If there is a big storm and you have downed power lines, your electric utility needs to know that those lines are de-energized before they send people out to handle them. So if your system is producing, the utility cannot de-energize those lines and make sure that they're safe. So your system could effectively kill the person who's working out to restore the grid. So many grid direct systems are configured such that if the utility grid goes down, if there's an outage, you stop producing automatically. That's kind of part of the arrangement of hooking up to them. If you want the advantages of a grid-tied system, but you also want your system to take care of your own power needs in the event of an outage, you have to go to a more complicated system known as grid-connected with battery backup, where you have a very defined disconnect to the grid, which will cut off in the event of an outage, and you have a second, effectively a redundant system that will supply your essential loads under those circumstances. So there's no way that you can feed power to the grid when it's down, but you have this second system that will meet your own needs. So lots of diversity in systems: AC/DC, battery equipped, not battery equipped, standalone, grid connected, and a combo. So let's take a look at what some of these systems look like. We're going to start with the simplest, the standalone DC systems. So here's our first figure is that pump out on the ranch or the sheep station where you've got a photovoltaic array and it's directly powering a DC load. There's some types of lighting that are DC that are powered this way. I think the highway departments use these for road signs and other types of working equipment. So just a panel, possibly a voltage converter, and then the load. Nothing else. So that's known as photovoltaic direct or DC direct. The next step up from that is what's known as a standalone DC system. So again, you've got your photovoltaic array generating DC power, and that will feed into a DC to DC converter, otherwise known as a charge controller, and this adjusts the voltage such that the current and voltage profile is ideal to charge whatever battery system you have, and every different battery system will want a different current voltage being applied to charge. You certainly want to charge as much as possible, as fast as possible, generally speaking. But electrochemical systems can only accept electrical energy and convert it to that chemical energy so fast. And if you try to give your battery system too much energy too quickly, it will find another electrochemical reaction to accept it that you might not have wanted, like hydrogen generation. So the charge controller ensures that that doesn't happen. So you can safely charge your batteries. And then on the usage side, when you want to draw electrical energy from those batteries, you'll sometimes have another DC to DC converter known as a load controller, which will ensure that the DC voltage that your service panel and hence your loads are accepting are what they need. Now, just a word about loads. I've kind of used that a few times. In terms of electrical circuits and power systems, a load, quote unquote, is any type of electrical appliance, a circuit, anything that draws electrical power. So your light bulb is a load, your stove is a load, your washing machine motor is a load, anything that uses electricity that requires current and voltage. So when we talk about loads, we're talking about the things we're powering with the system. Okay, what if we want to use standard appliances? If we go and buy any kind of electrical appliance, a refrigerator, a stove, most washing machines, almost anything we would purchase today for use in our homes or businesses is going to run on alternating current, and most of it will want a nice sinusoidal waveform alternating current, such as is produced by turbine generators, which power most of our utility systems. So in that case, no problem. We can still take our DC power that we generate from our photovoltaic array. We can adjust the voltage in a charge controller, store it in a battery. This is a standalone AC system, so we're going to need some battery storage because we might want to run something at night. Then, rather than going through a load controller, which is just basically a DC to DC voltage converter, we're going to take that DC signal and we're going to actually turn it into an alternating signal. And that's via a device known as an inverter. So rather than a converter, which just switches voltage but doesn't change the waveform, you still got a flat wave DC. This one we're going to go from just a flat time independent voltage signal and current signal to one that changes, periodic signal, alternating current, and of the waveform that we want to run our appliances. So the output of our AC inverter is going to be our service panel, and from that we can power several circuits, and this is effectively analogous to the type of AC service panel that you would have with a grid connected system, or just like not a renewable system, just a standard home power service panel. So a little bit more complicated than the DC system in that the inverter, which is now replacing your load controller, is a somewhat more complicated piece of equipment, but effectively serves the same purpose of interfacing between your storage and your loads. And in this case, not only does it match the right voltage, but it gives you the AC that your loads are running from. Last but not least, in the standalone category, we can do a bit of both. We can do an AC-DC combo system. Again, we're each time we go to a more complicated system, you'll notice we've got a bigger diagram. We're adding more equipment. So that is kind of the trend with any kind of home power system, any kind of power system. The more you want it to do, the more components it's going to have, the more prone to failure, the more expensive, but the more flexible, the more jobs it can do. So again, it's a balance of what you need for your site and your power needs versus your tolerance for upfront cost and risk. So if we need both AC and DC on site, say you're running a sawmill or you're running a business in a remote area, you want to supply all your own power, but you're running maybe some big DC motors. You don't want the inefficiency of taking your DC power you generate, storing it, and then converting it to AC, and then rectifying it and converting it back to DC. You generate it as DC, and you store it as DC in an electrochemical system. So you will get some efficiency improvement if for especially your larger DC loads, if you just use it directly as DC. So for that, again, We generate in DC from our array. We're going to use a charge controller and store that in a battery system, and then we're going to send it two ways. One, to our big DC loads. We're not going to bother to invert it. We're just going to use a load controller to adjust the voltage and deliver it right to our DC service panel. So we can run our big motors or any other big DC loads where inverting it and then rectifying it would be a big efficiency hit. Then we can tap that same battery system. May need to be a pretty big battery system, which is fine. You can add batteries as needed. We'll invert some of that, turning it into an AC waveform, and then run all of our standard AC appliances from that. So in the same facility, we can have both DC loads and AC loads being supplied from our same storage system, charged by our photovoltaic array. We just need to have these two critical pieces of equipment, our load controller or DC to DC converter for our DC loads, and then of course our inverter for AC loads. So one kind of trend that hopefully you're seeing is that the photovoltaic array is kind of the one component of a system, and the rest of your photovoltaic or solar electric distributed power system includes the storage, the voltage controls, the inverters, the distribution panels. Most of the components in the system are independent of the photovoltaic array or are external to it. I shouldn't say independent because they are interdependent, especially the inverter. But there's a lot more to the system, in other words, than just your solar panels that actually do the radiant energy to electric conversion that's so key to the renewable generation. There's a lot of other components that allow us to use that electrical energy in the most flexible and efficient way possible. So that's what makes up the bulk of a lot of these systems. Okay. Now we're gonna change course a little bit and look at grid direct systems. So these are the ones where if the grid goes down, so do you. So the first thing you'll notice is there's no battery storage, and we now have a utility meter connecting us to the power grid. So the most basic one is what's known as net metering. So you produce some DC power with your PV array, your photovoltaic array. You invert that directly. You don't store it. It goes to your AC service panel. Having inverted it, now it can either go to power your stove and your refrigerator and your washing machine and whatever, or if you don't happen to be using those appliances, it goes direct to the grid and goes through your meter and you get credit for it. So however many kilowatt hours or joules that you have produced in a given time, it goes out to the grid and you get credit for it. And then at night or on a really cloudy day when you're not producing enough to meet your needs, you will draw back from the grid and the meter charges you for each increment of energy that you use. And at the end of each billing period, you pay for the net amount of electrical energy that you used. If you generate more than you used in that month, a lot of utilities will allow you to carry that over as a credit for other months where you may not generate as much as you use. And typically at the end of the year, anything that you generated in excess of your use rolls off. So that's obviously a problem if you're looking to maybe recoup the initial cost of a system in savings on your power bills. You don't want to over-generate if that is your sole goal. And so that unfortunately will lead to people undersizing their system because they don't want to be giving away the power they generate. So one solution to that problem of people basically having to give their power back for free is the idea of the feed-in tariff. And this is actually a form of subsidies of renewable generation. And in this you use two meters that separately track the AC power that you have renewably generated and you are supplying to the grid versus the AC power that you are buying from the utility that they generated. And by using two meters, you can apply a different rate to each one of those. And in most cases, subsidies for these renewable systems will come in the form of a higher rate being paid for the power you produce and no limit to it. So however much power you generate, you get paid for the kilowatt hour. And then if you have to buy power, you buy power at whatever the going rate is. So you can make money on this dual meter feed-in tariff system. So that's an advantage that has, and that would, of course, incentivize people to go a little bit on the more generous side in sizing their arrays and equipment, because basically anything that they produce in excess of their needs, they could get some money for. Those types of, they're called feed-in tariff systems, are area specific, and in the US they are state specific. So they are available some places, not in others, but definitely a consideration for sizing your system if you're going to go grid direct. Both cases, again, if you need grid independence, if you need to have a source of generation independent of the grid, neither of these systems are going to work, because you are in both cases directly connected to the grid, and the utility will have to have a means of literally shutting down your inverter automatically in the event that these lines go down and your generation could energize a system that needs to be de-energized for safe work. Okay. So, obviously, what if you want the best of both? What if you want to maybe be able to do some net metering, or better yet, feed-in tariffs, sell some of your generated power back to the utility, or at the very least have the utility there to supply your needs in the event that you can't generate enough, which is a very real thing, especially at high latitudes and cloudy types of climates. But you might figure, well, for heaven's sakes, here I have a photovoltaic system and I can generate power. There's no need to be sitting in the dark when I can generate and the grid's down. In that case, you will, notice, have a more complex system, which effectively involves two loops, two different generation supply loops. And this is known as a grid tied with battery backup. It is grid tied, not grid direct. And it's only tied because we have a disconnect switch here, and we have only tied one portion of our system directly to the grid. The rest is independent. So when the grid is running, there's no downed lines. There's no reason for you to not be supplying to it. You will generate with your array, go through a charge controller, store that in your battery, and then your battery will supply an inverter. And of course, this is showing only an AC system. This could be configured to run like a DC system, obviously. But for simplicity, we'll assume we're going to run it all AC. So you will have one inverter, and then it will supply two load circuits. One is your main service panel that is directly connected to the grid. This will switch off. You will need an automatic disconnect switch, so if the grid goes down, it will sever its connection, will open the circuit between you and the grid, so you are now disconnected from the grid. Now you can run in standalone mode from your inverter to your backup subpanel, which you will wire to your what's known as essential loads, which are probably going to be quite a bit less than what you would have run using the grid. Presumably you in these conditions you may or may not be able to produce enough power to power everything. So you get to make choices about which loads are supplied by this subpanel. But the essential difference is this disconnect must be automatic, such that you can still run your inverter, but it decouples from the grid the microsecond the grid goes down, so that you are not putting energy into presumably downed or damaged lines. So you need to have that feature. You will have two panels and a meter, and of course you'll have your battery storage, and basically all of the features of a grid direct and a standalone system, plus this essential disconnect. So lots of options depending on what you need to do. Essential components, you will always have a photovoltaic array, of course, and you will have either voltage matching or voltage inverting features. You will have storage or not, and you will have a connection to the grid or not with different features. Okay, essential thing, what are we doing when all of these? We are producing and using electrical power. So let's just take a quick review of electrical power in terms of current and voltage, two things we can measure. The electrical power that is used to convert to torque and heat and other things that we need is the product, the mathematical product of current and voltage. So if I have more current at the same voltage, I have more power. If I have the same current at a higher voltage, I have more power. And if both my current and voltage are changing at the same time, I could have the same, more or less power, depending on which one is winning. Getting the product is getting bigger or smaller. That becomes important when we look at changes in irradiance, how much light per unit, sunlight per unit area is hitting your panel, and how hot it's getting. Because as we'll discuss more, a photovoltaic cell voltage, it's fixed by the chemistry of the PV cell material itself. Effectively, you can think of it that way, and it doesn't vary with sunlight. So you can give it all the photons in the world, lots of intense sunlight. That cell voltage is going to stay relatively the same, constant, the same. The current will increase. So you can think of it as one photon gives you one increment of current. Voltage, on the other hand, will change significantly with temperature, which tends to go hand in hand with times of greater irradiance. Think summer. So they're independent but related. So on the flip side, our photovoltaic cell current is the direct result of sunlight interacting with our material. So you can think of more sunlight, more current at the same voltage, unless it gets hot. So how do we go from a solar cell to an array? Well, one piece at a time, basically. Solar cells are manufactured from some kind of photoelectric material, usually doped silicon, although it can be made of many different types of materials. Some of the new architectural materials take advantage of electrochemical interfaces with dyes that are photosensitive and can produce the same effect. Lots of different advantages in applications, weight, flexibility, etc. We'll restrict most of our discussions to just plain old silicon, amorphous polycrystalline, and monocrystalline. These are the types of photoelectric materials that are used for home power systems and have the most use history. For more advanced architectural applications, these other newer systems definitely have a place, such as whole skyscrapers whose glass facing is photoelectric. You can probably find some references to those. Those are great. Home power systems, small business. We're going to mainly discuss the more mundane available solar panels. So regardless, they all start with some kind of solar cell. That's your unit photoelectric device. Silicon-based ones that are most of what is out there are about a half a volt apiece. Again, you can think of this being a chemically fixed voltage. Make the cell, it's got a half a volt kind of baked in, so to speak. It's not going to give you any current if you're not giving it any light, but it's got that half a volt just sort of ready to go as soon as we start hitting it with sunlight. So a half a volt is nice, but we tend to need a lot more to run most of what we run. And in fact, if you remember that your electrical resistive losses are dependent on current, not voltage, if we need power, we'd really rather have higher voltage and lower current to get that same P. Less I, more V in our P equals IV. So we would kind of like to have more than a half a volt, because otherwise we need way more current than we want to deal with. We'd be getting all our wires hot and melting them and just wasting a lot of power making heat. So we put those cells in series because, as you remember from your electricity basics, if we put sources in series, their voltages will add. So a PV or photovoltaic module manufacturer, such as Silfab Solar, who's right down the road from Bellingham Tech here in Western Washington, They take solar cells and manufacture panels or modules. So they will wire these cells in series, usually 36 to a module, so we have a nominal 18 volts per module. Then we can add the modules together in parallel or series to increase our current or our voltage as needed, and then keep stacking them up to make what we call an array. And that's what's actually deployed in your yard, on a pole, on your roof, or whatever. The array is what's referred to as the entire accumulation of photovoltaic material that's producing your power. So cells to modules to panels to arrays with increasing number of cells. Module selection factors. If you've gone shopping for PV modules, you can purchase them as a home user. You might have discussed them with a solar installer. There are a lot out there. Different styles, different construction methods, different types of actual cells. Polycrystalline, monocrystalline, amorphous silicon, non-silicon, etc. A lot of different things. Why do you pick one versus the other? Well, obviously budget's important. Some are more expensive than the other. You will pay for higher efficiency. You will pay for lower weight or more flexibility at the same efficiency. If you opt for lighter weight and more flexibility, you might have something that has a less favorable fire rating. So all that glass is heavy. If you go with a mono or polycrystalline system, these tend to be glass modules. You will need to have good bearing capacity of your roof or a structure that was designed to accommodate them, but it's going to be less of an issue with fire rating. It may be ordinary Class A rather than the electrical Class C, depending on the exact construction. Very important, the input voltage needed by your inverter will relate to your maximum power voltage rating on your solar cells, and your temperature response will vary. So all of these different factors are things that will be on effectively your purchase spec of your module. And just like buying anything else, understanding more of what you need and how those modules and your array interact with the next piece of equipment downstream in your system will determine maybe which module works best for you. So speaking of modules, you can imagine the fact that their current output is dependent on how much sunlight they're getting. How do you normalize these? How do you say this is a blah 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 watt max power module? This will give me so much current, so much voltage under what conditions? How can you compare them if they change depending on how much sunlight they get and what temperature they're being used in? Well, easy. There are standard test conditions known as capital STC. And these are standard conditions of photoelectric generation that are used to standardize, we'll use that word a few more times, different photovoltaic modules. So you can compare apples to apples when you go shopping for modules. So most important, standard test conditions, standard illumination. We're going to give the panel the same number of photons per unit area per unit time. And this is solar matched illumination. So STC illumination is 1,000 watts per square meter of solar spectrum intensity frequency response. You're going to do it at 25 degrees, and you're going to do it with a certain air mass density, 1.5 air mass, which very likely corresponds to sea level. So obviously if you have very dense air or very, very high humidity, you can have a little bit of scattering. You won't have quite as much intensity of this light hitting your panel. So by controlling these three things, any change in power generation response is going to be due to the panel, not due to the test conditions. So when you look at the label of your photovoltaic module and you look at what it can do, understand that that is at STC. So knowing that, what are the things that we might care about that are going to be our STC module characteristics? Well, since we're using this to produce power, power output's probably important, and since we know that electrical power is the product of current and voltage, it might be interesting to see a current versus voltage response at standard test conditions. So this is the relationship between the current output and the voltage output of a solar module being supplied with 1,000 watts per square meter of solar matched light. So if we short the panel, so we basically take the positive and the negative end of the connector and just put a wire across it, clip it together, short it out, it will effectively supply no voltage because it's shorted. You would know this from some of your circuit studies if you've done that. But it will give you as much current as it possibly can. So that is the maximum current production condition. There is no load kind of slowing that current down. And so this is called the short circuit current. So this is a measure of the maximum current that panel can provide. And it's known as I with a subscript SC for short circuit. Likewise, if we open the circuit, don't ask the panel to supply a single bit of current, it's going to give us the most voltage it possibly can. And that's known as the open circuit voltage over here. Since we know that power is current times voltage, which is effectively the area under this current voltage curve, we can define a point somewhere on this response curve that gives us the biggest area, the biggest square or rectangle that we can draw. And that means we're producing the most power. That's the current voltage area that you want to be in, or that point that you want that panel to be operating at when it's supplying you power, because you get the most power. If you went to a little bit higher voltages, you would roll down this curve and you'd still produce power, but less. You'd have a longer and lower rectangle, and likewise if you went to a little bit higher current, less voltage, you'd have a skinnier rectangle. You'd also have less area and less power. So this is an ideal power generation point in the current voltage response of your module, and it's called the maximum power point. And the voltage and current associated with that are called V maximum power and I maximum power, and those will be on your spec. And so both the maximum power PMP, the VMP, and the IMP are all specific to the way that module is going to act at standard test conditions. So be warned when you're shopping. If you're going to be getting that panel a lot warmer or cooler, or be giving it a lot more photons, you could get a value that's much larger or smaller. But this gives you, again, a basis of how much power you can get from any given panel. Okay, so let's take a look at some shopping, a shopping label, module label specifications. So this is a multi-power set of panels from a certain manufacturer. This is a fairly typical electrical data spec. Notice it says electrical data STC, meaning standard test conditions. And so you can buy various power ratings for this particular module type. And power output tolerance is a measure of how much each one of these will vary under different operating conditions. This is important for sizing your inverter and the type of efficiency you think you will end up getting. But for our purposes, looking at the voltage and the current at that maximum power point, you can see these are all listed and generally trend upward with power. And you can also see that the open and short circuit currents and voltages are listed. So if you look at for instance, your current at max power is 9.66, but your short circuit current is a little bit more. Likewise, your voltage at max power 36.8, but if we didn't expect it to generate any power and said you don't have to give me any current, the open circuit voltage is much more. And then module efficiency, This is a measure of the what's called radiant to electrical energy conversion. So for a given amount of radiant energy coming from the sun, which is going to be fixed to your location and your aspect ratio where you're going to put these, this is how efficient the panel is at converting that sunlight to the electrical energy you need. The higher this number, the better. And this is in percentage, so it's less than 1. You can increase this number generally by adding money. Definitely this is something you pay for, and regrettably having to give up other characteristics. So like any kind of engineering design, it's a trade-off. Okay, temperature effects. Summertime, we're trying to generate a lot of power. Maybe you're living in a hot climate, you want to run an air conditioner, or at least the motor for a swamp cooler, and you've got a lot of photons available. Life is good. Problem is your voltage associated with your maximum power point is going to drop, and this graph is pretty typical of the change in voltage as you go up in temperature. So for your standard test condition here, the 25 degrees C with the green curve, if we start to get warmer, say 40 degrees C, which really isn't that unusual in a warmer climate, or 60, which is totally imaginable for a black solar panel on top of a hot roof. We've now gone from a max power voltage somewhere up around here of maybe 18 down to maybe just 16. That is going to mean we have a much smaller rectangle. Our currents don't change very much. We lose a little bit, but pretty insignificant. So basically we have the same height of rectangle, but it gets skinnier. So we have significantly less power than we would have predicted from our max power at STC. Bummer. So there is a big benefit to keeping the panels as cool as possible. So we can add some cost by putting them on racks that offset them from the roof, allow some air to circulate. Obviously we can't shade them because then we wouldn't be getting the photons. Likewise, if you are in an area where you're going to rely on photovoltaics in the winter, you may not be getting as many photons, so you're going to have a flatter rectangle and you're going to lose on that side. But here we get a little bit of a compensation. Our max power voltage starts marching the other way. We actually get a bonus in our voltage, so we have a higher per cell voltage. That 0.5 goes up a bit. So at maybe minus 20 degrees C, you've got a solar panel working on your Antarctic research station. It's going to generate an awful lot of power if you can just get it some photons, maybe in the summer. This is important for winter systems. If you want to give yourself a source of power in the winter, know that the voltage that your cells are going to be providing to your inverter are going to be much more than what you would have predicted from STC, and certainly more than summer. So your inverter has to have a wide range of voltage inputs so that it can take advantage of all of that power you're generating in the summer, but you might be generating at a lower voltage, but will also accept all of the voltage that you're getting associated with your power generation in the winter, when chances are you don't have a lot of photons hitting your panel and you probably don't need to be cutting your inverter off at all then either. And guess what? A wider voltage input range on the inverter increases cost. So it's all a trade-off. But sometimes these things don't cost that much. So this is where having some supply chain knowledge and some good understanding of what costs, what doesn't, and what you need will help you make the most for your budget or your client's budget. So we talked about the effect of temperature. How about just giving that panel more photons? So what if we can keep the panel the same temperature, maybe, but just give it some more photons? Well, here's the effect of more photons. So this is increasing irradiance. So the green curve again is our standard condition, and it's pretty close to linear over most of the range. The fewer photons, the less current. It's pretty much 1-to-1. Luckily, again, we don't see, until we get very low, we don't see a big voltage drop. So it's, again, a trade-off. But more photons, more current, more power. Okay. Speaking of more photons or fewer photons, shading is not your friend. Definitely, in addition to simply having fewer photons overall, remember how the cells in a module are in series? So there's a joke about series connected Christmas lights that if one goes out, they all go out because you no longer have a continuous circuit. It's not quite so bad with series connected solar cells because they can, if they go into shade, such as we see here for these first two rows, remember everything's in series, everything's connected, they're still electrically continuous, but because they're not generating power, they're basically like a big resistor. So they're consuming power in moving the electricity generated by the other cells through them. So in order to basically reduce that resistive load from a non-producing cell, photovoltaic modules will come equipped with what's known as bypass diodes that can sense when we no longer have the correct voltage coming from a producing cell because it fell into shade, and goes, we'll just take you out of the circuit. So they're not giving you any power, these shaded cells, but at least they're not acting like big resistors. And generally on a 36 cell module, there'll be 3 bypass diodes. So each 2 long row loop can be taken out of the circuit as shade advances. Now, nice thing is if you have several modules, you could take a whole module out if it goes into shade. But remember, it's not producing now. So bypass diodes only partially compensate for the problems of having a cell go into shade and not be producing. It doesn't replace that lost production. Okay. Speaking of things being in series and parallel, we talked about being able to put our modules and multi-module panels in series and parallel. So just this slide is a quick review for those of you who have maybe not been in circuits for a while and need a little review of sources in series and parallel. Basic circuits classes quite often talk about loads, resistors being in series and parallel, and how current will flow through both, or will have the same voltage drop over a parallel-oriented resistors. Well, resistors are loads. Our photovoltaics, if they're producing, they're sources. The nice thing is they work the same way for voltage addition and current addition for series and parallel. So if you have 2 resistors and they're in series, the voltage drops over those 2 will be additive. Well, if we have 2 photovoltaic panels, which are voltage sources, and we put them in series, like you can see these 2 are, so you have negative, and we bump up 35 volts, and then we bump up another 35 volts. These 2 are in series. We'll add the voltages. Likewise, in parallel, we'll have the same voltage, but we'll double the current. And if you have an inverter or you have a charge controller where you need to supply it with a certain voltage, you can arrange the panels in your array such that your final net voltage is what you need, and you up the current to give yourself the power that you need. So this is an example of something where we have multiple cells in series. So you can imagine 2 of these panels with multiple modules in series, and then the two panels, the upper and the lower, themselves are in parallel. So we can up voltage by putting things in series, and we can supply more current by putting things in parallel. Okay. Let's go back to the sun, because if we can't get photons onto these modules, it doesn't matter how we connect them, we're not making any power. So at the end of the day, what we want is the maximum number of photons per unit time, per unit area of our panels to get the most power. And to do that, we need to understand literally which direction the sun's rays are coming from in the sky, so we can properly tilt and orient our panels. And we also have to have some kind of idea of how many photons per unit area per unit time we're going to get given our latitude and our season and maybe cloud cover and things like that. So lucky for us, there are a lot of excellent databases that we can tap that are location specific, and we'll go over one here at the end of this lecture. But this is just a little quick schematic to get an idea of words that are associated with which direction are the sun's rays coming from. The sun can appear to swing around the compass direction, east, east to west, south to north, and of course it will be higher or lower in the sky depending on the season and time of day. So the angle that the sun is positioned relative to you around the compass, north, south, east, west, is known as azimuth angle, and the vertical angle, how high is the sun in the sky, is known as altitude. So you can think of like going to high altitude, you're going vertically. Altitude angle is how high you are. So you can, for a given latitude, location, season, time of day, you can look up what are called sun charts to get an idea of where east-west the sun will be swinging. So this is the x-axis is literally a kind of flattened out compass, looking around the different degrees of compass. So true south is in the middle and true west is way over at the right, etc. So the sun will seem to swing from east to west, even if you're just looking straight south. And of course the angle in the sky will go up as we approach midday. That angle will be lower in the winter than in the summer. So this kind of gives you a visual idea of how you'd want to position your panel if you wanted to get maximum irradiance, the maximum number of photons hitting that panel straight on. And in fact, that is what you want. And this figure kind of shows this graphically. You want a 90-degree angle between the line of the sun's rays and the surface of your panel. That's going to give you the most light energy hitting your panel, and therefore the most electrical energy. So there's another graphic that kind of shows you why. So in the top you've got all of those sun's rays hitting your panel perpendicular, and you capture them all. If you take that panel for the same angle of sun's rays coming in, if you tilt it a little higher, you miss one. So the net irradiance on this second one is a little bit lower. And in this last one, you've oriented the panel flat. Now you're missing three of the rays. So the irradiance, the watts of sunlight per square meter, is going to be the least for this lower. So we want to know where the sun is in the sky at what time of the year, so we know how to orient our panels for maximum production, either annually or seasonally. And last but not least, a few vocabulary definitions. Irradiance is a power, watts of sunlight measured per square meter, usually square meter of your solar panel, presumably. Insolation is energy. So this would be joules per square meter or watt hours per square meter. So we can talk about an annual average. This area has more insolation, although the irradiance at a given particular time or season may be higher or lower. So irradiance is power per unit area, insolation is energy from the sun per unit area. And you can think sol means sun, so it's sun energy per unit area. Peak sun hours, or peak sun, is a power per unit area like irradiance, so it's power, but it's normalized to our standard test conditions. So if you talk about a peak sun, it's the equivalent amount of real time under your real conditions during which your irradiance will give you your STC 1000 watts per square meter. So if you're down on the equator at high elevation and you're getting 5,000 watts per square meter, you would need 1/5 of the time to get that STC as you would somewhere that's only getting 1,000. So the peak sun and irradiance are effectively equivalent, but peak sun is normalized to STC, and you'll see both of them. So we're going to take a little pause, and then we're going to come back and we're going to use a tool called PVWatts, which is a National Renewable Energy Lab tool. It's free, available to everyone. And we're going to walk through how to use all the concepts we've talked about with irradiance and where the sun is in the sky and maybe individual power needs to size the array or the amount of power, DC power you need to purchase for your array for two different individual use conditions. Okay, we are back and we're going to do some system sizing. So we're going to try to answer the question of how many photovoltaic modules do you need. And we're not actually going to get into determining the number of modules, but we're going to get to the one step that you would need before that, which is to determine the number of DC watts that we need in terms of generation power. Because remember, that's what our modules are ranked in or rated in, so many watts or kilowatts per module for max power. So we are going to look at what we need to figure out how many DC watts at max power we would need to buy. Then we just go shopping for solar panels and get however many we need to add up to that number, and then we can always go further and figure out how we want them combined in series and parallel, and do they match your inverter, and on you go. But you must start with, wait a minute, how much generation capacity do I need in my array before I can decide where I want to put it and how I want to arrange it. Obviously, if you are constrained in where you can put it, you might be starting with an area. I can only have so many panels. Here's how much power I can generate. But in either way, one of the key aspects of system design or characterization is going from what do I need, when do I need it seasonally, and how do I go from a DC watts that I can buy in the form of a max power point rating on a panel to what am I really going to get in the field with shading and dust and all of the derating or efficiency down rates of a real system. So again, we'll just walk through the steps here. So how many PV modules do you need? Determine the amount of electrical energy you want to generate and over what period of time. So a lot of folks who are looking at a grid direct system are going to say, okay, let's get all our power bills. How much energy, at least over the last few years, do I use on an annual basis? Maybe put some efficiency improvements in first. You might surprise yourself when you see how much power you're using. But come up with that realistic number and say, okay, I want to offset all of this so that my net metering says I owe 0 at the end of the year, then I would be looking at offsetting a certain amount of energy used over the year or averaging my power over the year. I might want to be able to generate power in the event of a grid outage. I might be looking at more of an off-grid or emergency supply. And in that case, I might look at the season when I'm most likely to lose grid power and say, okay, under the conditions at that time or in that location, what are the capabilities of my system? So then I might be looking at those targeted months where I'm likely to lose power. Is it in the winter if you've got high winds and winter storms? Or if you're living in the tropics, maybe you're going to be looking at hurricane season, which has some advantage because that tends to be in the summer. So the time you're most likely to lose grid power, you might be at your maximum advantage in generating renewably with a home photovoltaic. So either way, in a first scenario, grid direct, you're looking at a year-long average. In the second scenario, you have to look at the portion of the year in which you think you might need that off-grid generation. Number 2, how much of the power that you generate do you actually get to use? System efficiency. So here's where you get the depressing job of calculating all the losses. We're going to lose some losses in wiring and connectors, IR losses. The inverters we use have limited efficiency. Usually 96 is the best. 96% is the best we get. We're going to have to be realistic about module shading. As much as we would like to think maybe our modules are always in the sun, it's really easy for that our favorite tree or maybe our neighbor's fence post or a power pole or a stack, a roof penetration to start shading a module or two. It's never realistic to assume that we never have shade. We also need to look at the fact that we can get dust and other things accumulate that will scatter light such that it bounces back and doesn't get absorbed by our PV panels. All of these will downrate our system such that we will effectively need to generate more DC to get the AC needs that are reflected on our power bill. So these are what are known as efficiency knockdowns or derate factors, and we can use the PVWatts program to help us. The most important thing that we will use the PVWatts or any other online solar estimator for is to understand how much irradiance we're getting, and built into that in the case of PVWatts, temperature effects. So remember, our generation capability is affected by our temperature, because if we get our panel really warm, it's going to get hotter, we're going to lower our voltage, and so our max power goes down. So PVWatts will look at the average temperature on any given day and then ask you how you're going to deploy your panel and use some mathematical calculations to estimate what temperature you're likely to have gotten your panel and automatically derate your voltage for you. So you'll get a reasonable estimation. And then of course, latitude, longitude, season. The program will basically estimate how many photons of sunlight per unit panel area per unit time you're actually getting for your location. And it includes not only the effects of sun angle from latitude and season, but how likely you are to have a sunny day from local meteorology. And at this point, PVWatts has a little over 30 years of radiation temperature data. Obviously, if you are living in an area that is affected quite a bit by global climate change, past performance is not an indicator of future returns, and that includes photons. So you're going to want to be aware of whether or not anything predicted from even the best of calculators is representing what you're likely to see in the next 20 years. But it's certainly an excellent starting point. So we're going to go through two examples. One is a resident of Sacramento, California, who wants to basically not owe anything on their power bill. So they're looking at probably going with a grid direct system, and they're very cost conscious. They want to not pay anything for power. They want to be generating renewably, but they really need to buy only as much system as they need up front. So we're going to go through a little bit of information about what they need to generate, and then we're going to put their data into PVWatts online and then figure out what kind of tilt is best for them. And if you read the PowerPoints, you get the results of the analysis. I am going to go to PVWatts now. So I am going to keep my my data sheet over here to the side and refer to it so I can put input. So I am now showing my internet browser with my PVWatts. Resize some windows here so I know that you're seeing what I'm seeing. I also have my cheat sheet. Okay, so this is NREL, so pvwatts.nrel.gov, so that means National Renewable Energy Lab. So you can just type in PVWatts into your browser and it'll usually find this. So first we're going to find Sacramento, California. Sacramento, spell it right. And say go. Do a pause. Okay, we're pausing because I am using my bandwidth recording and also accessing PVWatts. Okay, so you can see that we are now looking at the PVWatts NREL data for Sacramento, kind of in the middle of town. You can zoom in a bit, taking some time, and you can see this little shaded rectangle is the actual geospatial area over which the data we're going to use is applicable. So, in some cases, the data we would get, the irradiance, temperature, probability of getting fog half the day might be very different on one side of town than the other. So this is a very good resource because of its very high geospatial resolution that can take into account these local things that might be really, really important for your particular site. So we also get latitude, longitude. So we know we're working at about 38 and a half degrees longitude. So that's where we are. There's our site. We're assuming we're kind of right in the middle of town. So next we're going to build our system. And because we don't know the system size we need, that's actually what we're solving for in this case. The DC system size in kilowatts is basically how many kilowatts of max power at STC of modules we're going to buy. So that's literally our array. So to make things easy, we're going to start with 1. Then we could just multiply that more or less by however many 1 kilowatt modules we would need, because that's a standard size of modules. So now we need to get some information about what kind of module and array type this resident would use. So we are going to assume that they're trying to save money, and so they're going to use a standard module. That means we're going to have a little bit less efficiency, and you can get a fabulous education by just clicking on these information buttons that are on every data input portion of this PVWatts program, and you get a great lesson, not just in what this program is doing, but in what is standard, and some information about these different types of modules, efficiency, benchmarks. If you click on the information and the help in this program, you basically get a complete education right there, contextually. So we can see they're going with standard. That means it's crystalline silicon, not amorphous. It could be polycrystalline. It could be monocrystalline. It's going to have a glass cover, good for fire danger, probably pretty heavy. And you see the temperature coefficient they're assuming. So basically those hot summer days when we're going to have lower voltage generation or cool nights, this is built into the program. So they're already telling you this is the coefficient they're going to use, and they're going to couple this with meteorological temperature data that's been recorded and that they're going to assume for that locale. Okay, and let's see. Now it's like we're reading off a spec sheet of what the owner of the residence does and doesn't want to do. They're going to mount it on the roof, and they're going to use an open rack. So you have different choices. You can mount directly to the roof, which means, of course, you don't get to adjust the tilt. It's going to get a little warmer. And if you have a freestanding system, you can opt for one that will track the sun. But we're gonna go for the open. And we can go down to advanced parameters, and we will assume the DC to AC size ratio is 1.3. This is a measure of how well your inverter and your module output couples, how often your inverter will cut out because it isn't getting the voltage it wants, other mismatch. And we're going to assume we have pretty much a top of the line inverter at 96% efficiency. Ground coverage ratio is not applicable here because we're not using we're using a fixed tilt and orientation rack. Okay, we're gonna assume that we're pointing due south, which tends to be the best, give you the best generation year round in the northern hemisphere. So azimuth, we're gonna leave that alone, and we're gonna leave the tilt at 20 degrees. See what we get. Now we get the depressing system loss input. So soiling, this is how much dust tends to collect. So we're going to bump that up from 2 to 3%. Sacramento might be a little dustier area. We're going to assume 15% loss for shading. These are efficiency reductions. So if these were 0, that would be good. So these are reductions from peak efficiency. At Sacramento, there's no snow. We're not going to assume any snow. We're going to assume only 1% mismatch loss. That's, again, the way your different system components interact with one another. Wiring losses, so that's your IR heating, your resistive losses in your wiring. We'll assume that that the customer is going to pay for some nice big conductors, so we're going to lose less. We're going to leave the connection IR losses at 0.5%. You just about can't get around that. Connectors are not perfect conductors. Light-induced degradation is the reduction in efficiency that comes with the system not being new. Systems will tend to overproduce versus their ratings at first, and then with time and exposure to light, they'll reach a steady state. We'll assume that's 2%. No change in nameplate rating. No age-related losses, and availability is the percentage of the time the system is offline for servicing or other types of monitoring. We'll call that 2%. So we end up coming up with an estimated system loss of 22.78%, not including the hit we're going to take for the DC to AC ratio and the inverter losses. So we've got that baked in now. So, and we're going to tilt this at 20 degrees. We'll probably need a rack unless it's a very steep roof, which is okay because we have one. So now we go to our results, and we're going to see how much power we get. So with 1 kilowatt of module STC rated panel production, we can get 1,416 kilowatt hours per year, which is a measure of how much more sun this area is getting, how much more irradiance this area is getting than STC, because we sure knocked that thing down 22% with resistive losses, which took away electrical energy that we could have gotten from our solar energy. And so we can see that there's a fairly big swing. We're not in the tropics, so we have a lot more solar radiation during the summer months than we do during the winter, probably a factor of more than double. And this is what we're looking for, our annual kilowatt hours per year. Now, if we wanted to keep the 20-degree tilt orientation, we would basically take our 7,000 kilowatt hours annually, divide it by this, and get the number of kilowatts of photovoltaic generation we'd need, and then divide that by the kilowatts per panel, and we'd know how many panels or modules we need to buy. But I think we can do better with some tilt. So let's go back to our system data, and let's try using a tilt that is more or less equal to our latitude. So let's go with 38.6. Generally, that is not a bad place to start. So remember, we had about 1,418 kilowatt hours for the year. So having tilted our panel up, you can see we got a good deal more. Not a huge amount more, but we got some more. So if you are going back to the PowerPoints, you'll find that if we use our sweet spot, and here's where if you want to adjust your tilt, you can just go back and forth like we're doing and virtually tilt your panel to whatever you think is the proper tilt. And as it turns out, if we use about 35 degrees, we hit the sweet spot, give or take, of AC energy. Turns out maybe it's a little bit less. Okay, so that would be the number we would go with, and then we can on the system we can go ahead and start effectively adding modules by adding our system size. So if we went to something like 5 kilowatts of effective module power output, we would end up getting a little bit of overproduction. So chances are the customer will need somewhere between 4.5 and 5 kilowatt hours to meet their needs. So go back, change location. So the 4.5 to 5 kilowatts of DC photovoltaic module generation would be your starting point for how many modules do you buy. You would look at the kilowatt rating of the module and do the math and maybe buy a number that would allow you to put them in the proper series or parallel configuration to match whatever inverter you had. So now you would be on to the component selection and configuration portion of the design, but you now know how big your array has to be in terms of photoelectric generation capability for your goal, for your system, your estimated system losses, and for your location. So we're going to do one more quick example. We'll end what turned out to be not quite so short a lecture. Let's look at somebody who needs to generate in the winter. So I'm going to use an area that is closer to Bellingham Technical College. I'm going to use Blaine, Washington. Now we're getting a lot further north. Oops. Typed that in a little bit wrong. Blaine, Washington. So here we go. We are way up north. We're overlapping into Canada. So here we are, much higher latitude, almost 50 degrees. We're 49, right on the border. Much wetter, much cooler. Okay. This is a different scenario. Now we're looking at someone who is interested in maximizing winter generation, as an off-grid emergency supply. You're looking at someone who's maybe living on the coast and is concerned that winter storms will knock out their grid power because of the high winds in this particular area, especially near the coast, and wants something that can at least keep the lights on, keep a minimum amount of home heating in a small, well-insulated building, and provide recharge to what's probably going to be a very robust battery system. So this person might be looking at, do they want to put more money into more battery storage or into a larger photovoltaic array that can recharge their a fewer number of batteries faster? So do you want to go with generation rate capability, or do you want to go with more storage? So understanding how much electrical energy you can produce in the winter when you would be using this system is important in understanding how to make that call for your system. Now, obviously, if we're talking about battery storage, the idea of the inverter is a little bit, why are we even using an inverter? Yes, in this case, we probably wouldn't even have the inverter. The PVWatts system info assumes you're using an inverter, very likely because this particular program was built up around a mainly grid direct demand. But if we put in an inverter and we make some assumptions that it's running very efficiently, we will at the very least be giving ourselves a conservative estimate of what kind of generation capability we would have. So let's go ahead and this time let's assume the person has a fixed dwelling that they want to provide for, and let's assume they're going to cover all of their roof area with photovoltaics, so they are roof size limited, and so they know they can fit 10 kilowatts of effective footprint of module on their roof. They know they need to produce a lot of power at a time that they're not getting a lot of photons, so they're going to go with a premium panel to get max efficiency. They're going to be using a fixed tilt, but they're going to use an open rack so they can tilt however they want. They're not going to constrain themselves to what their roof can provide. They're going to assume they are going to configure their inverter, if they have to use one, for a more ideal size ratio. And let's look at what we can assume for system losses for these folks, because they're in a little bit different situation. So these folks are still going to have 3% soiling losses. Example 1 data input. Nope. Did I just lose my audio? Hello? Yes, I still have audio. I'm going to pause and make sure. We're in the home stretch here, making sure I don't lose my audio for the rest of the recording, because it will be important to see the difference in this particular scenario. So we're going to go with less soiling. We're going to assume that this person is going to keep their trees trimmed back and they have a very clean roof line, so they can assume a little bit less shading. You see, they know they're up against a photovoltaic generation challenge, so they're going to optimize even more. They're going to end up enduring the same mismatch. They're going to opt for some very large conductors to minimize their wiring losses. They're going to go for a panel with less light-induced degradation, and they're not going to be taking the system offline very often during that critical winter generation time. So we have fewer estimated system losses, and a lot of that is coming from the 10% versus the 15% shading. Okay, so 20-degree tilt. Now we know that's probably not a realistic tilt, so we're going to start with tilt equal to our latitude. We're at a higher latitude. That's usually a good starting point. So now we're going to go to generation. So 10,851 kilowatt hours per year of AC coming out of their inverter. But here's the problem. If we're looking at these key months, especially December, where they're really afraid that they're going to lose their grid power, they're only going to get 372 kilowatt hours for the entire month coming out of their inverter. Now, that's not going to be a lot to charge their batteries with. So at this point, they're going to say, well, what's the one knob I have left to turn? I know it's winter. The sun at this latitude in winter, and especially around summer solstice, is going to be coming in at a very low angle. So we're gonna tilt that panel up to closer to vertical to see if we can't capture more photons per unit area on that existing 10 kilowatts of solar modules. And so let's see how much more we get. We had 3,500. So now we've gone up by almost 50. So if we were going to look at a fixed panel orientation that maximized our winter production, we could go up by a substantial fraction, not doubling it or anything, but we can go up by a substantial percentage by going to that more vertical angle. Now, what have we given up? We've given up annual production. So we went down quite a bit because now we are not optimized for in terms of tilt for those times when we're getting sunlight coming in from a higher altitude angle. But if this person is only concerned with the winter, maybe the 1,000 kilowatt hours of summer production is way in excess of what they use in the summer. And in fact, in many winter climates, a winter demand-dominated profile is pretty typical. They're going to want to configure and optimize their system to maximize those low numbers, knowing that that same system will be more than adequate to serve their needs in the summer months. So perhaps for this person, they'll be able to use their system to charge their batteries and give themselves an extra few days of battery life, saving some money on their battery storage system, and then that same PV system will have enough generation capability that if the grid goes down anywhere, April through October, they probably won't notice it. But again, their tilt that they will fix those panels to on their rack is very, very different than what it would be if they were going for year-round maximum generation as they would with a grid direct. So that's a couple of examples of what you can do with PVWatts. Again, highly encourage you to go through all of the information buttons and then correlate that to some of the information in the PowerPoints and get more of an idea of the important things that go into system design. and you'll see a lot of the same things and learn new things. So that is it for this lecture on our distributed solar electric for CENG 220 at BTC, or whoever you are listening to this. Hope you've learned loads.